Geodetic astronomy is part of geodesy.
It is the foundational element of all geodesy.
We've taken this system all over the United States.
Hello, and welcome to this panel discussion on astronomical techniques in geodesy, brought to you by the American Association for Geodetic Surveying. The American Association for Geodetic Surveying is a professional organization whose purpose is to promote a better understanding of geodesy and its application to land surveying and to geographic information science. AAGS's primary mission is that of education, and so to that end, AAGS has a series of videos that both explain geodetic concepts and their applications to practice. Perhaps the primary product produced by geodesy is that of highly realistic spatial coordinate systems, such as longitude and latitude, mapping coordinate systems like the US State Plane Coordinate System, and hiding systems. Geodetic astronomy is part of geodesy. It's the part that seeks to determine positions and directions on Earth by observing celestial bodies. Many people will recall that latitude can be estimated using the angle from the horizon to Polaris, the North Star. This is what enabled people throughout history to navigate vast expanses of ocean using the sun and the stars. Combining star angle observations and distance measurements enabled scientists to determine both the shape and the size of the Earth. This very early application of geodetic astronomy illustrates how fundamentally important such observations were to geodesy, and that work continues to this day. And so today, I have the pleasure of introducing our panelists, Mr. David Doyle and Dr. Ryan Hardy. Dave Doyle joined the National Geodetic Survey in 1972, and he held the position of Chief Geodetic Surveyor at his time of retirement in January of 2013. He was responsible for the development, technical design, and management of plans of programs that enhance the United States National Spatial Reference System. Mr. Doyle began his career as a geodetic surveyor in the U.S. Army in 1967 and served on numerous survey campaigns until completion of his military service in 1970. From 1970 until 1972, he worked for a private surveying company near Washington, D.C., where he was responsible for completing boundary, topographic, and engineering surveys while pursuing undergraduate studies in geodesy, cartography, and mathematics at the George Washington University. During his time at NGS, his experiences included all phases of geodetic triangulation, astronomic positioning, leveling, GPS data collection, data analysis, datum transformations, network adjustments, and data publication. Mr. Doyle's activities have included extensive efforts on the development and implementation of the national, horizontal, and vertical geodetic datums. He is currently the owner of Base 9 Geodetic Consulting Services. Mr. Doyle is a past president and fellow member of the American Association for Geodetic Surveying and is an active member in the District of Columbia, Maryland, and Virginia Professional Surveyors Associations. Dr. Ryan Hardy is a geodesist and geoid modeler at NOAA's National Geodetic Survey. He has a PhD in aerospace engineering sciences from the University of Colorado and a BS in physics from the University of Central Florida. Over his career, he has contributed to research in planetary astronomy, satellite geodesy, and geoid modeling. In 2020, he developed the Total Station Astrogeodetic Control System, nicknamed TSACS, a hardware and software kit that directs total stations to observe stars, enabling NGS to measure astronomical azimuths and deflections of the vertical. And so now, with the introductions out of the way, I'll hand it over to Dave for his opening remarks. Dave?
Okay. Well, thank you, Tom. All right. Well, one of the first things to consider in the use of geodetic astronomy and understand that in reality, it is the foundational element of all geodesy. Prior to the advent of the global positioning system, when institutions would start to create local geodetic frameworks, you had to start from something astronomical. And if we look at the National Spatial Reference System in the United States and the multiple horizontal datums that has included, the foundational data that begins with going back to Ferdinand Hassler in the 1816, beginning with coordinates. He had to perform astronomic observations to determine latitude and longitude. And it became a fundamental part of the description of the designation of the datums, simply to expand the reference frame, to ensure the integrity of the azimuths, the directions that were part of the standard triangulation network. And a little bit later, it gave us our first indication of what we now refer to as Earth orientation parameters, when it was discovered that the Earth really wobbles on its axis, and that was observed geodetically. One of the big things in the discussion of geodetic astronomy comes down to an element that regrettably not many surveyors are terribly familiar with, and that is, as it says here, the deflection of the vertical. A vitally important element in the science of geodesy. So when the user goes out and sets up an instrument, I don't care what you're going to do, whether you're running levels, you've got a total station, GPS, doesn't make any difference. When you level that instrument, you're actually leveled with respect to the geoid, to the local reference, to the local attraction of gravity. You are not necessarily leveled with respect to the reference ellipse, which defines our coordinate systems. And those angular differences are referred to as the deflection of the vertical. It's a north-south and east-west direction. And in terms of practical surveying that surveyors might actually see, it really comes down to an issue of changing the value of an astronomic azimuth. It's referred to as the Laplace correction. And what I've done here at the bottom, I've just given you a little cartoon here, which tries to show what this deflection of the vertical is about. But at the bottom, I've given you two examples, just in different parts of the United States, and to give you a sense of how these deflections can be radically different over a large and very complex and diverse country like the United States. So out Pikes Peak, for example, the Laplace correction, that is the correction you would apply to an astronomic azimuth to make it a geodetic azimuth, is almost 20 seconds, 19.6 seconds. Yet in Silver Spring, Maryland, at the headquarters of the National Geodetic Survey, it's only 2.7 seconds. So while these are important, they can certainly vary across the country. And the geodetic astronomy helps us determine what those values are and their relationship to the local geoid model. So Ryan's going to talk a lot about that. I'm going to give you some history on how the agency and its predecessor agencies went about performing these astronomic observations. So my first slide in that is just a series of pictures of some of the astronomic stations that the agency set over many, many years. Pardon me. For many years, they would actually build very significant monuments to host the instruments. I've got a picture coming up shortly. There are hundreds of these around the country. Right here at the top, I've given you a publication. I'll give you a link at the end where you can actually go and find, if you're curious, astronomic stations that were located in your area. Excuse me. But the ones you see here are fairly typical of the many stations that were established right up until about 1915. After that, the tendency was to observe astronomic positions, astronomic latitude, astronomic longitude, eccentrically to a known triangulation station. So we didn't go to the process of building these rather elaborate stone monuments. As you see, they're large because the instruments that were used back then were exceptionally heavy. And they required certain shapes to accommodate the techniques that were being observed. And I'll point those out in the next slide. And I've just given you a couple of stations here that are still around today. So if you happen to be in any of these areas and you want to see what they look like, you can easily go and find those marks. There aren't many left in the country, regrettably. Here's just a couple of images of the types of instruments that were used by Coast and Geodetic Survey right up until the time of about 1900 or so. We see the Meridian telescope, which was used, the large Meridian telescope on the left, made by Troughton and Sims in England in 1846. It's exceptionally heavy, and it was a wonderful instrument. Notice the crank at the bottom. That crank is used to actually lift the instrument so that you can observe 180 degrees. And if you'll go back to one of the slides I showed previously, you see some of the monuments that will have a space between them. Well, those spaces were set up so that it could accommodate that crank, that you could lift the instrument. Over on the right, you see a zenith telescope, which was used primarily for latitude observations. The use of the instruments, again, they were quite large and required a rather significant amount of training for any one observer to be able to perform correctly the measurements that were required to help us support the development of the horizontal framework. A little bit later on, we see changes to the instruments themselves. They're doing the same functions, but now they're a bit more miniaturized. And I say that only somewhat mockingly, because if you look at the picture on the left, it's a Bamberg theodolite. It was considerably smaller than the two instruments that I showed you previously, but I'd like you to note the array of instruments that were used, simply to perform an astronomical observation. It's not just the instrument itself, but notice all the equipment that's associated with it, particularly the chronometer. So this was a rather excessive amount of effort that had to go into performing these measurements. It was one that was done with great care and would oftentimes take weeks and in some cases months to perform if the surveyors were in an area where you had a lot of cloud cover. The Bamberg theodolite was the primary instrument for Coast and Geodetic Survey right up until the early 1960s, when it was replaced by the T4, the very, very big brother to the T2 that many surveyors are used to. The T4, first of all, it's quite heavy, weighs about 90 pounds when you put it all together, comes in 4 boxes. And it had a very distinct advantage in that it would actually turn on the horizontal direction, which made it a lot easier to orient the instrument in the meridian to perform high accuracy latitude or longitude observations. It was a critical element to make sure that you were in the meridian, that is a line that goes from the North Pole to the South Pole and passes through you. And the T4, because it actually turns on its horizontal axis, was quite an improvement in that. The Coast and Geodetic Survey, National Geodetic Survey used that right up until the last observations that the agency did were performed in 1985. By then, GPS had pretty much taken over the development of the horizontal reference frame, although I'm pretty sure it was still used by the Defense Department, back then, which was the Defense Mapping Agency, for several years thereafter. But for a practical purpose, NGS stopped using the T4 in 1985. One issue that comes up, and this is where I think it's important for surveyors to at least have a fundamental understanding of the difference between an astronomic and a geodetic position. It's an interesting description, but this has come up in several occasions fairly recently, actually, in my little world. So what I've given you here is just an image showing a station in Tacoma, Washington, Tacoma Astro Station 1892, and I've given you its deflection components on east, west, north, south, and its Laplace correction. And below that, I've given you its astronomical latitude and longitude and its corresponding geodetic latitude and longitude. And notice that the positional difference is in the order of almost 150 feet. This is kind of important, I think, for surveyors to at least fundamentally understand that these are different, simply because much of the foundation of the public land survey system of the United States was derived astronomically back in the 1800s, as were the boundaries of quite a number of states. So a couple of quick examples here. I recently had occasion to offer some discussion to a person dealing with the southwest boundary of the state of Pennsylvania that had been determined astronomically by the Coast and Geodetic Survey in 1892. And there was a horizontal positioning and an astronomic position that had been determined. The person who was looking at this data had asked a local surveyor if they would perform some GPS measurements at the monument, and which they did, and found positional differences on the order of about 200 feet, from which the surveyor estimated that the monument had been physically moved. Well, no, that wasn't the case. It's simply the fact that the astronomic position and the geodetic position were roughly about 200-foot difference at that location. Another example is the Four Corners mark that many surveyors have heard of. The Four Corners, where the four states come together. Not too long ago, there was some consideration that, the mark had been set in the wrong place. Well, of course, that was not really the case. But when you go back and you investigate how it was actually established back in the 1870s, the surveyor who performed those measurements, a gentleman named Chandler Robbins, he began from an astronomic station down near a place called Shiprock, which is about 25 miles away. He began at an astronomic station, then ran a traverse up to where he believed was the appropriate intersection of the coordinates that had been given by the Congress to determine the location of the Four Corners. Well, the astronomic position of the place at Shiprock has an uncertainty of roughly about 350 feet, considering the time it was done, the instrument that was done. So it's important, I think, for surveyors to have at least a basic understanding that these coordinate systems are different and how the science of geodesy helps bring them together and how we look at them historically. I mentioned earlier that using geodetic astronomy allowed us for the very first time to detect part of what we now refer to as Earth orientation parameters, how the Earth moves. Well, in this particular case, a German astronomer had noticed that his latitude kept changing. And in the 1890s, the Coast and Geodetic Survey and the International Association of Geodesy took this up and created a series of observatories in the Northern Hemisphere, all at 39 degrees and 8 minutes. Excuse me. 3 in the United States, Gaithersburg, Maryland, Cincinnati, Ohio, and Ukiah, California. Here you see pictures of them and the instrument that was designed to be used. And their whole function was to do nothing except determine astronomical latitude. They used the Horrebow-Talcott method, which was the standard kind of method for determining astronomical latitude. And from that, we could determine how much the actual pole differed from what we perceive as the rotational pole. Excuse me. This was a very distinct, important element and in the creation of contemporary geodetic reference frames. The agency stopped doing that in 1983 when these technologies were replaced by more agile space-based programs such as VLBI and of course GPS. There's just an image of what the polar rotation looks like, roughly about 9 meters over the course of about a year and a half. The other important aspect in geodetic astronomy was the observation of azimuth or direction. And any number of surveyors have gone out and performed solar observations, even a few have performed geodetic measurements, Polaris observations. And what I'm showing you here are simply probably the 3 most popular instruments that were used certainly by the National Geodetic Survey and other geodetic institutions around the world to determine azimuth direction. The T3, the VILD T3 on the left, a 2/10 second theodolite, the T2, a 1 second instrument, which we use for lower order observations, and the Kern DKM3A. I particularly find the Kern instrument to be very intriguing. I always enjoyed times when I got to observe with that. But those were the particular instruments that I think were fairly universal from the 1950s on until GPS replaced the contemporary use of triangulation. And surveyors who have occasion to go back and look at the accuracy, the integrity of azimuths or directions, I often refer them to looking at these instruments and particularly looking at the style, the capability. In this case, 2/10 or a 1 second instrument. I've known many surveyors who want to go out and do this with with something that's a little bit less precise. So encouraging them to use the best quality instruments they can, and then to follow the best quality directions or how you go about performing these observations. And what I've provided here is simply a link to the standards that are still in place to this day, the standard specifications for geodetic control networks. And if you peruse through that document, I've given you the URL, you can go and download it. What you'll find, if you are in the mood to perform, let's say, a first order astronomical azimuth, first of all, you're going to have to use something like the T3 or the DKM3, a 2/10 second instrument. And I point out 16 positions of the circle. That's direct and reverse with a standard deviation of the mean of only 0.45 seconds. So it's quite a rigorous set of observations that you have to go through. But nonetheless, the development of observations by latitude, longitude, and azimuth were the 3 primary elements that were a significant component part of building classical triangulation networks literally around the world. Today, with the advent of GPS, of course, we have considerably easier technologies to go about and perform that. But as you're going to hear from Ryan, one of the key elements that we worry about today are the issues of our geoid models, the deflection of the vertical, and how we can improve them now using some of these improved astronomical techniques that he's going to talk about. So I will pass this along to Ryan. I've given you here a couple of corrections that were appropriate for the observation of azimuths. And lastly, I've got some references here that if you're interested in following up with anything dealing with geodetic astronomy, here are a number of excellent resources that you can go through. And if you have any comments or questions, you can always post them to the Ask a Geodesist at AAGS, and we'll be happy to respond to you. I'll pass it on to Ryan now. Ryan, take it over.
All right, thanks, Dave. So let me pull up my screen. Great, we're looking at that. So I'm a geodesist and a geoid modeler at NGS, National Geodetic Surveys. I've got a PhD in aerospace engineering sciences from University of Colorado, and I studied physics and astronomy at the University of Central Florida. And when I was studying physics, kind of discovered that what I loved most about it was orbits and gravity. And that kind of led me to study geodesy and spacecraft navigation, which is what eventually led me to NGS. So I mainly do geoid modeling for NGS, but I also dabble in instrumentation. And I also do some occasional field work, as we see in this photo here. So a few years ago, I developed what we call the Total Station Astrogeodetic Control System, or TSACS, to command an NGS-owned total station to observe stars, record video of those stars, and also record the angles of those stars over the horizon. And we use that data to estimate the deflection of the vertical. So why does NGS care about the deflection of the vertical today? So the short answer is that the deflection of the vertical gives the slope of the geoid. So if you're not familiar, the geoid is just a three-dimensional level surface, an equipotential surface that Earth's gravity forms that best fits mean sea level. It's set up in a way so that the direction of gravity is always perpendicular to the geoid. Therefore, the deflection of the vertical captures that direction of gravity, or the geoid slope. So if you have a model of the geoid available to you, ellipsoidal heights that you get from a GNSS receiver can be used to compute orthometric heights above sea level. Since water tends to flow from high orthometric heights to low orthometric heights, this makes the geoid a great basis for a height system. So this is why NGS is going to transition the United States to a geoid-based height system called the North American Pacific Geopotential Datum of 2022, or what I'm going to call from now on NAPGD 2022. NGS, we're targeting this geoid model accuracy of 1 centimeter, which is a very ambitious goal. But that means that you're going to be able to use GNSS height measurements to get orthometric height measurements anywhere in the United States accurate to 1 centimeter. So our models are currently online, and they're being evaluated by the user community, and you are welcome to visit our website to play with them yourselves. Now, the crown jewel of NAPGD 2022 is the model we call Geoid 2022. This is what it looks like, at least for the North America Pacific domain. This is a quarter of the Earth's surface that we're looking at, and this is really just a map of how far Earth's gravity is pulling mean sea level, or our understanding mean sea level, away from the reference ellipsoid. And the typical value of that deviation there, that what we call the geoid undulation, is about plus or minus 30 meters. The geoid is, of course, the sum of many different gravity contributions from distant sources, and that makes a relatively smooth surface. So you can see that the major features of it are relatively large scale, covering thousands of kilometers. So fine scale features tend to get smeared out, and what we mostly see are these large scale mantle features deep beneath Earth's crust. We can zoom in and see a little more detail in the contiguous United States. The geoid peaks around negative 10 meters near Yellowstone. And you can see some hints of mountain ranges and maybe the continental shelf. But we could also look at the deflection of the vertical itself using our DOV model, what we call Deflect 2022. Since this is the slope of the geoid, it reveals a number of fine scale features. So when we look at the slope in the southeast or northwest direction, as we're looking in here, what we're kind of doing is just hill shading the geoid. And this reveals a lot of relief. So the geoid slope, or the deflection of the vertical, has a typical value of plus or minus a few arc seconds or a few centimeters per kilometer. So you can see here mountain ranges, ocean trenches, continental shelves. You've got big rough features in the west, like the Basin Range and the Grand Canyon down here. And running through Iowa, we've also got this very interesting feature called the Mid-Continental Rift. But what I want to emphasize is that the deflection of the vertical reveals quite a bit about the geoid and the gravity field that contributes to the geoid. So since deflection of the vertical directly measures the slope of the geoid, it's a solid way to check if our model of the geoid is accurate. So if you've got a bunch of DOV measurements lined up with close spacing, and by close spacing I really mean about a kilometer, maybe at most 10 kilometers, you can add up all of those implied geoid slopes and assemble profiles of the geoid. And this is exactly what NGS did in the 2010s with our geoid slopes validation surveys, which are these 300-kilometer profiles in Texas, Iowa, and Colorado. So in these surveys, astronomical techniques were used alongside leveling, GNSS, and gravity measurements to produce geoid profiles that are really the primary source of validation for our geoid models. These are how we check the accuracy and verify that 1 centimeter target accuracy of our geoid models. So clearly, DOV is very important to NGS even today, but how do we actually measure it? So you really need 4 ingredients, and first you need to establish the vertical with something that's free to swing and align itself with gravity. So you need something like a pendulum or a fluid. Maybe that's a natural horizon. Maybe that's a compensator, an instrument. And second, you need a device that can relate to that direction of the vertical to a well-known star. So that device usually takes the form of a telescope, a camera, theodolite. And finally, you need to know two other elements to predict where that star actually is, what direction that star actually corresponds to. And so that means you need to know where you are, what's your actual geodetic position, and then what time is it? What's the actual rotational angle of the Earth? And when I say rotational angle, I really mean three different angles, all of which are dependent on time. So these days, GNSS solves the problem of time and location. But in the days before, people would use telegraphic signals and radio time signals for transmitting time, and triangulation for establishing position and differences in position. So suppose you can use your time and location to predict the angle of a star above the horizon. You could also measure what that is in the field. So the difference between what you predict and what you measure in elevation angles gives you the deflection of the vertical in the particular azimuth that you're facing. Now, deflection of the vertical is really, again, two components. So if you want to get both of those angles, you have to do multiple star observations. And that's the simple explanation. So as Dave has shown in the previous presentation, NGS and its predecessors have done this kind of observation for over a century. The manual star observations required were slow, and they required very bulky instruments. So a DOV observation for a single site would ideally take an entire night. And for a number of reasons, surveyors and geodesists eventually stopped using this technique in the 1980s. However, interest in the geoid drove NGS to look at this technique again for measuring geoid slopes. Now, when we did the geoid slope validation surveys, we borrowed this state-of-the-art Swiss Zenith camera, and that was perfect for our purposes. But if we wanted to do this on a regular basis, we really needed our own system. So it turns out we have sort of these updated versions of the theodolites that David presented earlier. We've got a Leica TS60 robotic total station in our inventory. And it can measure elevation angles to about half an arc second. So we figured that we could program this total station to point at stars, record video of these stars, measure their elevation angles, and we can take those measurements and use them to estimate deflection of the vertical. So the end result of that was TSACS, again, the Total Station Geodetic Control System. So it's just a hardware kit that directs our TS60 to record video of bright stars. And in just 15 minutes, we can measure 25 stars and get a 0.2 arc second DOV solution, something that would take our predecessors an entire night. Now, 0.2 of an arc second is a geoid slope of about 1 millimeter per kilometer. That makes it a really great tool for geoid validation. On the right, you can see 4 frames from a video stream showing a star, and then you see a little flash from the GPS control timing light that we use to actually establish what time it is in the video stream. And this is what the setup looks like. Inside this control module on the right, we have this consumer-grade GPS receiver to establish location and time. We've got a microcontroller to talk to the total station and tell the total station what to do. We use a Raspberry Pi, a single board computer, to act as a data collector for the video and angle data. And these hardware components are very simple and lightweight. The user interface is just a single green button and these indicator lights. That's it. That button just tells the system to start and stop the observation. And it is as simple as that. And here's a more detailed look at the hardware. And I just want to point out how inexpensive these electronics are. This is hobbyist equipment that we put together for under $1,000. So in addition to deflections of the vertical, we've also done some experiments observing astronomic azimuths. So this involves shooting a terrestrial imaging target, this target up top, and also Polaris in the same span. So the goal here is just to use the same video technique to measure the horizontal angle between Polaris and this imaging target. And the conventional way that people orient a survey network these days is basically by taking 2 GNSS occupations a few hundred meters apart and using that to orient a network of observations. Unfortunately, this only really buys you about 3 arc seconds of orientation accuracy, and that translates to about 1.5 millimeters over 100 meters. With our astronomical techniques, we're really leveraging this optical precision. So we can orient to local survey networks close to 10 times better than GNSS orientations, closer to 4/10 of an arcsecond, or 2/10 of a millimeter over 100 meters. So we currently use this technique on our vector tie surveys at space geodesy sites around the United States. So we've taken this system all over the United States, including Alaska, Hawaii, the DC area, and the Mississippi River. Here's some photos from some of those surveys, but especially Hawaii, Alaska, and Louisiana. I myself have gotten to go on a number of fun adventures, particularly in Louisiana and Alaska. And you may hear more about those in the near future. Now, finally, Dave has talked about the practice of geodetic astronomy in the past. And I want to talk about what I think about the future of it may look like. So at NGS, where we want to continue to maintain using this technique to maintain the geoid in NAP-GD 2022, and DOV is well suited for that. So DOV is perfect for linear corridors, since you can directly recover the geoid just by stacking together different observations. So rivers, valleys, coastlines, those stand out in particular. Now, rivers combine commerce, population, and natural hazards. So those three together to drive a demand for accurate orthometric heights. So ideally, we'd love to get DOV geoid profiles on the Hudson, Mississippi, and Columbia rivers. The second facet of the future geodetic astronomy is instrumentation. So the best measurements come from zenith cameras right now. And zenith cameras are just large telescopes with very sensitive inclinometers that capture a large number of faint stars at the zenith or directly overhead. So our friends at the National Geospatial Intelligence Agency recently acquired a new zenith camera, which they call Vampire, that outperforms our system by a factor of 5. Now, improvements in accuracy and precision, they're going to come from building new and better zenith cameras. And while zenith cameras deliver the best quality, we also want to see if there are fast and cheap ways to observe deflections of the vertical. They don't require the purchase of a new total station or a zenith camera. These are very substantial purchases. So what are some cheap alternatives? So geodetic astrolabes are lightweight, tripod-mounted combinations of inclinometers and telescopes. And the telescope is mounted at fixed angles, so the mechanics of it are very simple. And there are a bunch of examples of geodetic astrolabes from the 1960s and 1970s, and even examples of people using leveling instruments to do these kinds of observations, just with a mirror in front of the telescope to redirect the line of sight, so we could perform DOV observations again, which is level. Now, these can be built relatively cheaply. Now, cheap systems mean that we can get data from a wider variety of contributors, including hobbyists and citizen scientists, which could be very valuable in the future. Finally, I just kind of want to highlight the biggest operational limitation for planning DOV campaigns, which is the weather. We can't see through the clouds, and that makes it challenging to do these observations, especially in coastal settings. So there's also a real safety and administrative challenge to doing night work. Now, one way around this is combining GNSS signals with leveling at short baselines. And people have certainly done this before, but maybe there are other ways that people can do this. And it's just something to think about. Now, I just want to close with the note that geodetic astronomy is very much alive at NGS. It's a crucial ingredient for validating our upcoming height system. And it's part of our workflow for tying together space geodesy measurements at various sites around the country. It's really the most fun part of my job. And I really want to thank AAGS for the opportunity to talk about it in more depth. Thanks.
All right, thank you both very much for those presentations. And now what I would like to do is to turn it over to some of the AAGS members we have in our audience so they can ask you some questions in this panel discussion.